So let's take this idea of travel graphs and apply it to our calculus that we already know. So displacement, in maths you'll often see us use the pronumeral x for displacement. I think in physics they tend to use s. Yeah, it doesn't matter, it's just a pronumeral at the end of the day. So it's distance from a point, but the difference is it has direction. So you can think of it as left and right or so on. So often we think of travelling along a number line, and so if it's negative we're travelling to the left, and if it's positive we travel to the right. It doesn't have to be that. I mean, you can define positive and negative to be in any direction that you like, and we will end up doing that in some of our more interesting problems in extension 2. It makes life a lot easier sometimes if you make positive down rather than positive up and things like that. Changes the equation, of course, but velocity then, well, v is an obvious notation for velocity, but velocity is the derivative, because remember, derivative is rate of change, and we just said that velocity was change in displacement over change in time, so it's dx to t. Now, there is another notation, this dot notation, we can use for the first derivative, but we tend to just use it only when we're talking about motion. So x dot, its first derivative, or velocity, because we're talking about motion. It's the rate of change of displacement with respect to time. Now, it's speed, but with direction. So negative, I'm travelling to the left, positive, I'm travelling to the right. Now, acceleration. A, again, an obvious notation, but it is the rate of change of the velocity with respect to time. So v to t would be a notation, which therefore means the second derivative of displacement with respect to time would be a notation. And using the dot notations, x double dot can represent acceleration, or v with a single dot, because it's the first derivative of velocity. So they're all different notations that you might encounter. So it's the rate of change of velocity with respect to time. Now, acceleration is an unfortunate word because, look, displacement, I can say, oh, it's distance with direction. And velocity, I can say, oh, look, it's speed with direction. Well, acceleration, it's, it's acceleration with direction. It's the same word in both. So, yeah, but again, watch out for this word, deceleration. There's no such thing as deceleration. Okay? It doesn't exist. Okay? What deceleration is when your acceleration is in the opposite direction to which you're travelling, forcing you therefore to slow down. Okay? It probably makes more sense when we talk about forces rather than acceleration. Force, of course, being mass times acceleration. If I'm travelling, say I'm travelling this way, I'm going in the positive direction, and someone pushes me in the back, so my acceleration is positive, well, I'm going to get faster. But if someone pushes me in the front, pushes me backwards, I'm going to go slower. So I still have an acceleration, it's just in the opposite direction to which I'm travelling. Now that does not mean that negative acceleration is slowing down, because if I'm travelling in the negative direction and my acceleration is in the negative direction, I'll go faster. So it's just in the opposite direction to which we're travelling. Oh, here's a lovely little diagram I saw once in the newspaper, so I thought I'd share. Oh, look. To get from displacement to velocity, you differentiate. And therefore, logically, to go back the other way, we integrate. Isn't that a nice little picture? Okay. Now, so here is a travel graph. But this time it's displacement versus time rather than distance versus time, and that's why we've got the negatives there, you'll see. We talked about average velocity before, but average velocity is not necessarily that useful. I mean, if you get pulled over by the police, now that some of you are driving, and he says, "Sir, do you realise what speed you were travelling?" And it might be, say, you're in a school zone and you're doing 100. Naughty, Aidan, naughty. Right. He's not going to listen to the argument and go, oh yes, but if you go over the past hour, my average velocity was 35. He doesn't care about that. So when we're talking about our graph then, the instantaneous velocity is the slope of the graph at that point. Now, if we're talking about a curve, as we saw when we were doing our curve sketching, that's the slope of the tangent. So if you want to find the velocity at a particular instant, it's the slope of the tangent. So the same thing would carry through to a velocity time graph. So if you have a velocity time graph, then if you want to find the instantaneous acceleration, it would be the slope of the tangent. Now notice, by the way, these are the same motion. The first one, the displacement time, well, it looks a bit like a cubic. Hence, when I differentiate a cubic, I get a quadratic, so I get a parabola. And you see things like, well, hang on, velocity is equal to 0 at stationary points. So at the peak here and the trough here. If you go down to the below, oh, sure enough, that's when velocity is 0 on that graph. So you can translate from one graph to the other to draw, if you have the displacement graph, you can draw the velocity graph and vice versa. Well, let's draw the acceleration graph, and what we're expecting to see, well, if I differentiate a parabola, I should get a straight line. So there's the acceleration time graph for that one. Okay, same sort of questions as we saw with the other travel graph. Distance travelled would be 7 metres. I've gone up 2, I've then gone all the way down to -2, and I've gone back up 2, well that's meant to be -1 there. Total displacement, on the other hand, is -1. I've ended up 1 unit in the negative direction. Average speed would be 7/4, distance over time. Average velocity, displacement over time. Okay. So now we don't actually need the graph. It can be handy, but if we've got the equation, we can just use our knowledge of calculus to solve these problems. So our formula is, as long as we've got the equation of that curve, whatever the graph is, we're right. So displacement time, and we're going to find a formula for acceleration. I just got to differentiate it a couple of times. Differentiate it once, I got a formula for velocity. Differentiate it twice, I got a formula for acceleration. So when is it stationary? Well, it's stationary when velocity equals 0. That's the first derivative. And fortunately, what an amazing coincidence, we call them stationary points. Oh, it's stationary at stationary points. So we know it's when velocity equals 0. Solving that equation, it's stationary initially, and again after 14 seconds. That's how people think, whoa, hang on. If initially you're stationary, how then does it move? Well, then that all comes down to the acceleration. I'm standing here still, but someone pushes me, well, I'm going to start moving. All right, so another particle moving on our x-axis, how handy. Starts at rest, t equals 0, but it's going to start not at the origin, but over at x equals 7. Its acceleration at time t is 2 plus 6t. Now we want to find where it is at t equals 3. So I have a formula for acceleration. I can find a formula for velocity by integrating. Don't forget your plus c if you're doing it this way. And it becomes very important, our constants now. So I can sub in the initial conditions to work out the c. In this case, had you forgotten your constant, you would have got away with it because the constant turned out to be 0. So it'd be 2t plus 3t squared. So now get a formula for displacement. Again, integrate. This time though, you wouldn't have got away with it. Constant turns out to be 7. I have an equation now for displacement, so I can sub in and we get 43. So after 3 seconds, particle is 43. Now, however you want to say it. You might say, oh, it's at x equals 43, or you might describe it like I have. Oh, it's 43 to the right of the origin. Of course, that's going through all the effort of finding a constant. I could do it this way. Acceleration is dv to t. Separate the variables. Match the limits. So when time is equal to 0, velocity is equal to 0, I want to find a formula that links time and velocity. If I do them as definite integrals, I don't have to worry about forgetting to find the constant. So the left-hand side, well, anytime you're going to something from 0 to that something, you get the thing. What a wonderful definition. So V will end up being, sub in from t to 0, because there it is, 2t plus 3t squared. Now I can get that one do the same thing, but with displacement. So when t was equal to 0, displacement was 7. We want to find its displacement when time is 3. So sub in, I'll get, on the left-hand side, I'll get x minus 7. And on the right-hand side, we end up with whatever 3 squared plus 3 cubed is, but move the 7 over, and we get our 43. I personally think it's a much neater way of doing it. And as I say, I don't have to worry about forgetting the constants and so on. All right, let's look at HSC one. Much more interesting equation. Displacement time, it's still displacement time, but we now have a hyperbola if you think about it. T minus 2 over T plus 2 would be a hyperbola. Displacement when t equals 0, so all right, very straightforward question. So we're 1 metre to the left, or at x equals -1, however you want to say it. Show that, because remember I just said it is a turnip paper, so they might not pick up on it. So they give them a nice little gift question and say, oh, look, show that. And then hence go and find velocity and acceleration. So all right, 1 minus 4 on t plus 2. Ah, that would be t plus 2 minus 4 on t plus 2. What do you know? That's t minus 2 on t plus 2. And again, as I say, it is a turnip paper. So what they're basically doing is trying to make the question a lot easier, because you can see people going, oh, well, I'll go and differentiate this, and you've got to use a quotient rule and all that. Well, it's much easier to differentiate the 1 minus 4 on t plus 2. So x is 1 minus 4 on t plus 2. Differentiate it once, well the 1 goes to 0 of course. I can use my reciprocal rule, minus the derivative on the function squared, and so we end up with 4 on t plus 2 squared. I can also use the reciprocal rule to find acceleration now, minus the derivative on the function squared. Or of course you could just put it in index form, you can do it that way as well. We get minus 8 on t plus 2 cubed. Okay. Is the particle ever at rest? And I know you love these sort of questions. Give reasons. Explain why. There's our velocity formula. Is it ever at rest? No, that can't equal 0. So particles, I don't know if that's a great explanation now I look at it. I say, because I'm essentially saying, oh, it's never at rest because it's never at rest. Possibly I should say something like, oh, well, the fraction can never equal 0 because of this, that, and the other. What's the limiting velocity? Okay, so if it's never at rest, what's the limiting velocity as t? Well, okay, so we're basically saying, what's the limit as t approaches infinity of velocity? So it's just a limit question. Think of the graph. I find that probably the easiest way of doing it, but it ends up being 0. But as I say, if you think of the graph, there's the graph, and then it's very obvious what the limiting velocity is. You just look at the graph. Oh, look, the asymptote is 0, so that's where it's off to. Okay, let's do another one. Particle, straight line, again, that's very handy. Oh, a bit of trig. X equals sine 2t plus 3. This is a sneaky way of getting people to draw a trig graph. So rather than just simply having the question, draw this sine curve, they go, let's draw a graph of displacement versus time. Essentially, you're drawing a trig graph. So if I'm drawing a trig graph, amplitude's 1 unit. We've shifted the whole thing up 3. The period would be pi. I'll mark off my divisions every pi on 4. So there's my axes. I'll just dot in a line at 3 because I've shifted that point that it winds along. Sine graph, we would normally start at 0, 0. This one will start at 3 because we've shifted up 3. Then we would go up, down, up, down, up, down, up, down. And we get a lovely sine graph. Okay. So part 2, using your graph, or otherwise, because maybe your graph's no good, find the times when the particle is at rest. Well, I'm just going to look at the graph. It's at rest when velocity is equal to 0. We know it's when the derivative is equal to 0, but rather than solving it, I'm going to say, I'll just look for the stationary points. off the graph. So t equals pi on 4, and it was an x equals 4 at that time, 3 pi on 4, 5 pi on 4, 7 pi on 4, and in our domain that was all the stationary points. Here you go. Describe the motion completely. You get to show off your English skills. Okay. So what did I say? Oh, I used some big words. Look at that. Oscillates. The particle oscillates between x equals 2 and 4 with a period of pi seconds. All right. Oh, good. We did manage to get through all that.